You know that huge gold chandelier-like structure you see in videos about quantum computers? Yeah, that's just the refrigerator. Quantum computers could usher in a revolutionary transformation across industries like biology, finance, pharmaceuticals, material sciences, engineering, cybersecurity, and more, thanks to their potential to solve complex problems much faster than the computers mostly used today. We're frequently told that nothing will be the same in the quantum era, but these quantum systems are also incredibly sensitive, and their efforts can easily be slowed down or sabotaged by even trace amounts of heat. Actually delivering on the quantum promise will require operating quantum computers in near perfect conditions, meaning really ridiculously cold. Unlike regular computers, most of which can still operate at temperatures well above even the hottest day ever recorded on Earth, quantum computers have to be kept at extremely cold temperatures, colder than the North Pole, colder than the dark side of the moon, colder even than the Boomerang Nebula, the coldest natural environment in the known universe. That's just 1 degree Celsius above absolute zero. I wanted to find out why quantum computers needed to be so cold, how such temperatures are achieved, and why we might need to go back to the moon in order to make it happen.
So the main reason that people cool down quantum computers is that they want to be able to run it faster and also access the sort of hidden quantum properties that actually are hidden under thermal noise that we have at elevated temperatures.
That's David Gunnarsson, Chief Business Development Officer at Bluefors, a company who specializes in making the specialty refrigerators used to make quantum computers so ridiculously cold. Before we get to the how and the why, I'm going to give a brief overview of what puts the quantum in quantum computers. Timestamps down below if you want to skip ahead. Classic computers use things called bits to transmit and store information. A bit is short for binary digit, something that exists in one of two possible states. This is usually represented as true or false, positive or negative, most commonly 0 or 1. Physically, these bits could be represented as an electrical current that's either on or off. But if you've ever seen or read the sci-fi story, The Three-Body Problem, there's a scene where they actually use an army as a type of computer, with each person representing a bit by holding up either a black or a white flag to perform complex calculations. This brings me to qubits, or quantum bits, the infamously sensitive little units at the heart of a quantum computing system. And much like classical bits, qubits can also be represented physically in many different ways.
A qubit could be an atom. I think that's the most natural quantum system we know. Of course, atoms was the thing that needed quantum mechanics to be explained. But then you also have this other side, which is sort of a little bit more exciting, because we actually don't use nature's own quantum systems. We actually engineer quantum circuits. That was actually what got the Nobel Prize last year in physics.
Ultimately, a qubit is anything that can be in one of two states or both at the same time. This includes light, physical atoms, and specially engineered quantum circuits. These quantum systems are very sensitive to disturbance. Something as tiny as one stray photon or rogue atom could come crashing through like a bull in a china shop, causing errors in the output. That's where these big gold chandelier-like refrigerators come in.
The Chandelier is the dilution refrigerator, so that's the core technology of Bluefors. We can start with why we use gold-plated sort of material. It's not just to look nice. It's actually we use a lot of copper in the system, because copper is a very good thermal conductor. And that's why it's sort of used as a base material when you do cryogenics. It transports heat very easily away, but copper oxidizes very easily. So that's why we actually gold plate it. It doesn't sort of create the bad surface. And then the reason why it looks like a chandelier is it's actually many coolers in one, but then it's actually cascaded with different coolers going up to room temperature.
When these chandelier-like coolers are actually in operation, you don't see them. They're behind thermal shields and also inside a vacuum chamber, so stray particles aren't causing mayhem inside the quantum system at the bottom. However, they are a great visual, which is probably why they've almost come to represent quantum computers in popular culture.
And a dilution fridge is actually a quantum system in itself. It's actually using two isotopes of helium. So you have helium-3 and you have helium-4. It turns out when you cool those down below 1 Kelvin or below, they actually start separating because one of them becomes a superfluid. It's a liquid that actually have no viscosity. But then you have the helium-3 that doesn't become superfluid. And it turns out that they are like oil and water. They don't mix. So when they don't mix, they actually create two sort of phases, it's called. One is called a diluted phase, which means that there is a little bit helium-3 and helium-4 diluted in each other. It's a little bit like having sugar in water. And then you have an helium-3 rich state. And it turns out that when you take helium-3 away from this diluted phase, the system wants to restore. If you just take away helium-3 atoms, you actually cool the environment.
I want to pause here just to point out that helium-3 is extremely rare and expensive on Earth. So much so that some companies are planning to go all the way to the moon just to harvest some and bring it back. More on that later. Quantum computers are one of those technologies that people often say feels like it's always a decade away. But Gunnarsson reassured me that more progress has been made in the last few decades than most people may realize.
When you look at the qubit, you usually measure the quality of it in a lifetime. How long does it stay quantum? And back then, it was a few nanoseconds, the lifetime of the system. And if we look now, 26 years later, you now have 1 millisecond. So it means that the coherence time or the quality of a qubit have improved more than a factor of 1 million. When you start scaling the number of qubits, you need to, of course, find the right processes to actually keep that quality for all the qubits. But then when you have that, and the complexity is solved, then you actually do have this 100 to 1,000 qubit platform. And that's when the fun starts.
You can check out our video on helium-3 harvesting on the moon right here. And if you've got more quantum questions, let me know down in the comments. I know I sure still have a bunch. Many principles of quantum mechanics are brain-breakingly counterintuitive, but I love learning about this stuff almost as much as I love sharing what I learned with y'all. So please smash that like button down below and subscribe for more stories that make you say, what the future?